It's night now. I guess it's good afternoon for you or good evening for me. It's 8 p.m. here. So, Frank, let me ask you a question, really short question. So, most of participants here are undergrad or professors. Can you let me know? Just to make
So here, yeah, it's a
yeah.
mixture of probably 70% professors
Oh, okay.
and 30% students.
Oh, that's good. So I'd like to thank again Professor Frank. So it's really nice to have this opportunity to talk to you. It's my first time doing a webinar, so I'm really sorry about anything not going okay, my microphone or something like that. So I'll talk today about the supramolecular systems for drug delivery technology. A couple of hours ago, I talked to Frank and said, "Oh, I guess I made a huge seminar, but I will try to be not fast, but make my point." Okay, so I'm a head of laboratory, the Sistemas Polymerics and Supramoleculares. So it's a supramolecular and polymeric laboratory system. So in Department of Physics and Chemistry in Federal University of Itajubá. So first of all, let me point out where we are located. So we are in the southeast of Brazil. Can you, when I hold my mouse, can you show the arrow in the screen, Frank, or not? Okay, I assume you can. So in the first picture here in the left corner in the top view. So here is Minas Gerais. We are located in this state. We don't have ocean view, all this stuff, the outside of Brazil. But in Minas Gerais, we like to receive people and make barbecues, have some picanha frank, okay? So more specifically, Itajubá is located here. It's really close to big cities like Rio de Janeiro, São Paulo, Campinas, and Belo Horizonte, our main capital of the state. And Unifei, I will call Unifei the university. It's this picture down here. It's the front view of our wall. In the back side of the wall, you can see these cartoons here. They made some pictures of people which was important to Brazil, like scientists and people from the university. And more specifically, my lab is located in this small building, the orange and green building. So it's a biomaterials building. We have our office here and labs in the first floor. So let's keep going. I started my lab in 2013 with 3 brilliant students, Bruna, Clara, and Angelica. And after that, since we got our graduate program in chemistry started in 2015, the group get a little bit bigger. So I start to advise some masters and PhD students. As soon as 2016, the group get a little bigger than 2015, and I have now Felipe in my hands, my son. Now he's 4 years old, big boy. And time was passing. In 2017, a big party with my lab and Juliana's lab, my wife. She's a theoretical chemist, so we are always together working and doing some research. I will show you something like that. And 2018, 19, the group get a little smaller. The funding from Brazil was reducing anyway. But we are anxious for the picture for 2020, the 2020's pictures, because now we cannot stay together. So lab nowadays are doing some research, including supramolecular systems, inorganic complex, electrospinning materials based on polymer fibers, and hybrid materials based on inorganic compounds with organic molecules, especially mainly using electrospinning device. So Here we can have some examples from a PhD student, Larissa. Okay. Larissa, PhD student, I will show this data with cyclodextrin supramolecular systems, core sheet fibers from Maria Cecilia, also a PhD student, finished in 2019. Larissa finished in 2018. These two beautiful pictures with different colors here, and the shining glove here down is from Flavio, a master student. Now he's a PhD student. Electrospoon fibers was something I have learned from MIT with Mingling Ma, a PhD student at the time, now a Cornell professor. And now here, down here, I have the opportunity to show something like these photochromic fibers, a paper that Frank Alex is a co-author with us. So I'll start talking with you guys about the supramolecular system. I will not introduce a lot about supramolecular system. It's not a new idea. Jean-Marie Lane, Pedersen, and Tran they were laureated in 1987 with the Nobel Prize, and they have developed and used these molecules with structure-specific interactions of high selectivity to interact with different gases. I will call gases from now on. And this supramolecular systems is specialized mainly by no covalent interactions. So among many examples of molecules that can form or assembling to do some supramolecular systems, cyclodextrin is one of the most used ones. I mean, most used, especially based on some characteristics that cyclodextrins can present. So cyclodextrins are this kind of structure, these truncated structures. They are based and they're constructed by glucose units. And depending on the number of these glucose units, cyclodextrins can have different characteristics, including solubility, FDA approved, something like that. So here I can show you guys the beta cyclodextrin. Beta cyclodextrin is assembled by and connected by 7 glucose units. It's one of the most used one. Beta cyclodextrin is FDA approved for oral drug delivery. So you can also hear down here something like some examples of papers from 2007, 19, and they are all reviews that you can find something like including historical aspects of cyclodextrin. So you can find the discovery period, the investigation. So the discovery period when cyclodextrin was discovered and was started to be characterized. The investigation it was the time that cyclodextrin started to be analyzed and identify their structure. And we are here nowadays, the application. I will show you some applications from our lab. And this kind of applications can get more complex using something like polymers and other device. But we start with the simplest ones. When we start talking about cyclodextrins, we can call cyclodextrins a host. As I showed you previously, cyclodextrin has some important characteristics, especially about their exterior. It's a hydrophilic exterior with a hydrophobic interior. So this difference between hydrophilic and hydrophobic at the same molecule are able to interact with gases. And these gases for us in this seminar will be pointed out as drugs and to form these kind of supramolecular structures. The supramolecular structures are held together based on non-covalent interactions between the cavity and the hydrophobic part of the molecule. And this equilibrium between host and gas isolated with the supramolecular system can be achieved based on some characteristics. We'll talk about this a little bit further. So why I'm talking about cyclodextrin with drugs? Not just because I like this and was my master's and my PhD thesis, but when you look to the numbers on the Scopus database from 4080s in 2020, most of the papers here, number 2, when you use the keyword cyclodextrin drug, is the reason why this kind of superstructures has been used to drug delivery. So cyclodextrins with polymers has a huge number of publications also, but cyclodextrins and drugs is the most impressive numbers when you search for this. Okay, when we think about the equilibrium in our system, our inclusion complex or supramolecular system have been administered orally, nasal, or different types of administration. And inside our organism, this kind of superstructure start to dissolve and the gas is released from the cavity of cyclodextrin. Cyclodextrin then start to interact with other molecules in our body and the gas go to our bloodstream. So we now need to understand how it works, how you can understand the equilibrium between inclusion complex and host gas systems to prevent some problems or to improve the drug delivery system. And how can we do that? So to make this kind of supramolecular systems applicable, we need, in my point of view, we need to understand and use our lab and our knowledge to understand this superstructure or the structural characterization of the system, and also the thermodynamics, or I mean the parameters that can be control these superstructures. So when you talk about thermodynamics, we're talking about the effect of temperature, for example. And I will show you guys one more slide before. So we have this kind of possibilities to form this inclusion complex. So when our host and gas systems start to interact, they can form which we call 1-to-1 ratio supramolecular system, or also other supramolecular systems can be achieved 1-to-1, 2-to-1, 2 hosts with 1 guest, 2 guests with 1 host, or 2-to-2 ratio. So how can you manage, or how can we understand this system? How can we prevent it? We need to understand that to propose a better drug delivery device. So when you look at this, it starts to be some points you need to take care. When you think that the only possibility is to form 1-to-1 system, it's not true for most of the supramolecular systems. When you look to some papers, and not from my group, but from other ones, we can place the cyclodextrin in different sides of the gas molecule. So here I point out a system, cyclodextrin with sertraline, an antidepressant molecule, and look at the possibilities. We have 16 possible interactions, at least between cyclodextrin and the gas molecule. So which of them is interacting for sure and going to our drug, our medicine, and will be administered. So I will start now to show you something. It's not new, the papers, but I like this job. Joel is the first also for sure. He was a master's, and this work is from his PhD in Federal University of Minas Gerais. I start calling this sertraline trilogy, uh, not because he split the publication, because the for sure the research was starting in 2010 and was evolving like uh, like episodes. So I put this like this in this way, and I hope you enjoy. But was three nice papers from his PhD using the same molecule, beta-cyclodextrin, with the same gas, sertraline. So the first episode and second one was published in International Journal of Pharmaceutics, a key one journal, and the third one in Chemical Engineering Journal. It's a high impacted journal. So Joyce, the first character, the main actor of this paper. I was just hoping and helping him with this all this stuff. So when I start taking the literature about cyclodextrin, the first I need to understand is why using cyclodextrin. Why should we associate cyclodextrin with a drug molecule? So most of this case is to improve the drug solubility. As soon as you get this improvement, drug can be more absorbed, and then we can reduce the doses or something like that in our organism. So the picture in the left side show a graphic, a general one, it's general, for concentration of the drug and concentration of cyclodextrin. Most of the cyclodextrin systems with drugs are AL, we usually say AL1, but here is just AL system. That means that as much as cyclodextrin you can include in this supramolecular, in this solution, more drug you can dissolve. So the first test he ran out was something like put some amounts of cyclodextrin, which has a low solubility in water and buffer, with a solution of cyclodextrins, or even just the water or the buffer. So in this first graphic in the right side, we can see that at pH 2, cyclodextrin has a solubility lower than 2.5 mils. And when we include these into cyclodextrin, more or most of the sertraline can be dissolved. So we can increase the solubility of sertraline from 2.5 milligrams per mil to about something like 12 or 13 milligrams at pH 2.0. So when you associate these in water, the concentration of sertraline in solution grows so tremendous that goes something like 30 milligrams per mil. At pH 7.5, all systems are pretty much like insoluble, even in the concentration at bigger concentration of cyclodextrin. So based on this first result, we can think and go forward and starting to investigate sertraline with cyclodextrin, because they are probably interacting solution, and that solid material in the bottom of the vial are going to the solution and interacting in water or buffer. So I'm not sure if all of you are familiar with, but one of the most powerful ways to measure this interaction is using isothermal titration colorimetry. This kind of equipment is a highly sensitive equipment to measure heat flow when you titrate a solution of gas or host, depends on the concentration do you want or the system, in the solution of the other one. So when we start titrating this solution in another one, the heat flow can be measured by ITC and you can get the thermodynamic parameters. So based on all physical chemistry, fundamental physical chemistry, you can get the all thermodynamic data directly, almost then directly. So we can see that the interaction is spontaneous and both are based on the enthalpy and entropic favor. And most important here, not in most of case, but here, we can measure the binding affinity between both molecules. So the number shows that the binding affinity is about 5,000. So it's a huge affinity between these molecules. And look at the N number. N number is the stoichiometry. So when you're thinking about stoichiometry, you're thinking about if our system is interacting 2:1:1, 2:2:2 ratio, all that possibilities. So the number 1.3 is quite weird because it's not a 1:1 system and not a 1:2:2 system. Anyway, so we start thinking about these numbers and start doing some structural characterization as soon as you get the thermodynamic data. So based on the structure characterization, the most powerful technique to use is NMR. So NMR in 2D NMR, we can find the position of the hydrogens, and based on this experiment, we can see which hydrogens are close to other ones. So I can figure out which hydrogens from cyclodextrin in the interior or exterior are close to the hydrogens from sertraline. So, but in this system, we can find these two possibilities at the same time, that both rings from sertraline are interacting with the cavity of cyclodextrin. So we now start thinking about what's happening. So thinking about the numbers of ITC data, and we are not able to figure out how to deal with this problem. And then a collaboration with Juliana, theoretical chemist, and also my wife. I told her, please, can you run some calculations for me? And she made some DFT calculation at the time, and she told me, okay, we have 16 possibilities. And I told her, okay, do it. And okay, it will take so long. Don't worry, you have a week. And she told me, no, I don't have a week. I have 2 or 3 months to do all these calculations by myself. I told her, okay, find a student. No, I don't have a student to do that. Anyway, 1 month later, she ran many of these calculations, and she brought me some data and told me, okay, based on your data and my data, these 3 possibilities can coexist in equilibrium. 2 supramolecular systems based on 1:1 host gas system, and another one based on 2 host and 1 gas system. So from now on, we want to think, and since we know the interaction and possible structures, Joel start thinking, so I'm not the physical chemistry guy, I would like to go further. And I said, okay, go ahead. What do you want to do? And he started thinking about something like in solid state, because he was talking to me, and at that point he told me, we cannot give to the animals or anything like that something in solution, or how can we give the sample. So we usually produce these supramolecular systems based on freeze drying process. So let's understand what's going on in solid state. So he made so many analyses based on thermal analysis, X-ray, infrared, even scanning electron microscopy. And all these analyses point out that the supramolecular system exists in solution. And at that point, he told me, okay, I should find somebody to collaborate and do some in vivo experiments. At that point, I told him, in vivo experiments for antidepressant drug, I don't know no one. So, but he found a professor from south of Brazil, and Stella Hatz, and she was running some models based on, I'm sorry, based on the tail suspension test. So you administrate the drug to the rat, put a tape in his tail, and put upside down. So the rat usually wants to run away from the situation. So if the drug started to let the rat like dizzy, I don't know if the word is that, but the drug's not getting the antidepressant effect. So they can measure the immobility time. So as soon as the immobility time is shorter, it means that the antidepressant model is working. So he took so much samples. The airplane went to the south of Brazil, and he almost got caught by the federal police because he was taking samples from drugs and all this stuff without declaration. Anyway, but when he got the results, was something like impressive, because using a supramolecular complex at 1-to-1 ratio or 1-to-2, the effect of immobility time was better than free sertraline. And to understand this, he got some data from mass spec to quantify the sertraline in plasma, and he could figure out that after 30 minutes, sertraline from 1-to-1 ratio of this inclusion complex was much higher in the blood sample, in the plasma concentration, than the free sertraline. That's why the immobility time was much better. And he was, oh my God, so I can got my second paper published, and what's the question now? He's really, really clever guy, clever. Now he's a researcher in a private company. Now he's running his own company, actually. And what's the next question? He was, okay, we are doing so freeze drying process, and all this freeze drying process take too much time to get the complex ready. So basically, when we are talking about freeze drying or complex, we get amount of cyclodextrin solution, sertraline in solution, get these mixed together, froze the sample in liquid nitrogen as faster as we can, and then freeze dry. This freeze drying process takes about something like 7 days to dry just 200 mils of sample. Could you imagine something like in a company doing some, oh my God, something like 5 liters, 10 liters, or more than this? So he was, okay, I want to use the spray drying from the lab and get this ready in 30 minutes. And I told him, let's go, I can help you. And at that point, he runs some spray drying. I call here conventional spray drying. You'll see later why. And he got all the samples ready in 30 minutes. And he told me, see, I told you, I can get this faster than the freeze drying process. And I just told him, okay, take some samples, go to the NMR and see what's going on. So you can scale up the process in the season finale, but we need to know if it's for sure if you got the inclusion complex. Then he went to the NMR facility and get the NMRs. The first one, we can barely see some cross-peak correlations between sertraline and cyclodextrin. This means that the sertraline and cyclodextrin are not interacting, and this was get from the spray drying process. And I show him the freeze drying process sample. See, we can see all these cross peak relations. That means sertraline is included in cyclodextrin cavity. So he was a little bit upset at this time, and he was thinking about what's the difference between this process. So spray drying is based on heat to dry your sample, and freeze dry is based on cool the sample prior to dry. So he was thinking about that, and he told me, I will solve this problem. And he went to the NMR facility again, took the samples, and run some different NMRs at different temperatures. So when he got all the spectrum and showed me and something, I was really impressed, because when he was decreasing the temperature, the cross peak correlation started to show in the contour map. And at this point, he was talking to me and he said, okay, I will modify the spray dry from the lab. And I told him, you should talk to the big boss so he can tell you if you can do this or not. But he do something really clever. Instead, going to the right side of this diagram to the conventional spray drying, he used two different pumps and passed this solution, different solutions, to a device to get the solution homogeneous. And prior to go to the spray dryer, he controlled the temperature to inject in the spray dryer. So here he called something like SDLT, from spray dry low temp. And with these samples, he got some really beautiful microparticles of the inclusion complex, and he did so many ITC experiments to show the binding affinity. Is the left graphic in the top view. So showing that the binding affinity is bigger at low temp than the higher temperature. And when he went again to the Stelhardt's lab to see what's going on in vivo, he runs experiments and in vivo experiments using sertraline, SD samples, just spray dry, and SDLT. So when you compare the data from plasma concentration of sertraline, the SDLT is quite similar to the freeze drying, so he could make something really fast and with the same efficiency in vivo. So he got a patent on this process, all this stuff. He was really successful in his PhD. So after that time, I got a position and went to come to Itajubá, and the work must continue using cyclodextrins. It's something like I really like. It's not something like shiny and colorful like these dyes, and that's why it's difficult to find some students to work with some thermodynamic data. But until then, we have something like this. So we have the sertraline molecule interacting with cyclodextrin, and all this stuff is based on thermodynamics. But in 2016, a student, Larissa, a PhD student here in Itajubá, started to question me. So you're saying all this stuff, this is important, but the medicine we buy in the pharmacy, it's not just cyclodextrin and the drug. We have so many other excipients inside the medicine. So if you put something like excipient with the system, I told her, yeah, you probably get a problem. So now we have something like more complex. we have cyclodextrin interacting with a gas molecule, and in solution we have this new gas molecule. Which one can interact with the cavity of cyclodextrin? Will be probably the gas molecule with the big K. If K2 is bigger than K1, the binding affinity, so all that proposition, it's not working anymore. So she started doing the PhD and proposed something like this, using two different molecules. She did not use sertraline because it was not allowed to buy to get these samples based on Brazilian law. Anyway, so we find something to test. So she used atenolol and losartan. Both are antihypertensive drugs. And combining these molecules with cyclodextrin, she got this inclusion complex. This was prior published by other groups, atenolol and losartan with cyclodextrin. But now she adds something new. She adds SDS, the sodium dodecyl sulfate. So when she add this in solution, what she get? So she run a lot of ITC experiments, a lot, using different temperatures. So this three graphics here is for the atenolol ternary system, as we call. So she start titrating and SDS with atenolol, the red dots, and no interaction between these molecules. When she titrate SDS with beta-cyclodextrin, the blue ones, she got this kind of heat flow between the interaction. And then when she titrate the SDS with the atenolol complex with cyclodextrin, she got the same kind of curve, titration curve. This was intriguing to us because what's happening is the atenolol being displaced by the SDS. Once again, I asked Juliana. I should put some acknowledge to her here. Juliana, can you, my wife and the researcher in the UFM Unife, can you run some molecular dynamic simulation for us? And she asked me something like, which kind of system do you want? How many water molecules do you want? And I told her, I don't know, you can run, you know all the theoretical calculation, I don't know nothing. So my system is this and my problem is that. So she and her PhD student, Guilherme, run a lot of calculations. And in gray, we can see the atenolol inside the green molecule, cyclodextrin. And the beginning of the simulation, the SDS was outside of the cavity. After some steps of the molecular dynamic, SDS was fighting for the cavity with atenolol. And then SDS finally could displace the atenolol for the cavity and get inside of the beta-cyclodextrin host cavity, which was not observed for losartan. Losartan, during the titration process, the curves when we titrate SDS and losartan, the red dots, okay, no interaction between them. However, when you titrate the SDS with the losartan complex, the black dots, you can see it's not similar to the SDS beta-cyclodextrin interaction. So she did so many calculations too. And during the start, the yellow SDS was outside and the losartan was inside of well, it's not yellow, it's red actually, the losartan. It's not gray, it's red inside the green cyclodextrin. And even during the whole time of the simulation process, SDS could not displace losartan from the cavity. So comparing these both systems, we get in a position that even each system can be acting differently from each other. So a more deep investigations should be done, not just only was like the sertraline ones. So when we start the next slide, I was thinking to improve, because when you're thinking about sertraline or losartan, all this material for drug delivery system using cyclodextrins, I was thinking that all this freeze drying or spray drying process could be not successful. And so we start thinking about polymers to not get a sustained release, but a real control release system using cyclodextrins and drug molecules. So we started using the electrospinning. Was something that I have learned with Ming Lin at MIT a long time ago. And then we can get some fiber mats like these ones, micrometers or nanometers in diameter. This can be used in many ways. And here in the lab, you are using in these two ways. When you use uniaxial or just mix all the polymers, cyclodextrins, or polycyclodextrins. Here is a polymer based on cyclodextrin cavities with the drug in the same solution. And we can get something like dispersed drugs in the fibers. Or we can do something like a core shell fibers. So we can use a shell polymer, biocompatible with a nice degradation time, or inside the core, the cyclodextrin or the polymer of cyclodextrin with the drug. So we can get these two situations in the lab now. And this is an unpublished result we have using losartan and PLGA with polybeta cyclodextrin. PLGA is a hydrophobic polymer, and polybeta cyclodextrin is a hydrophilic one. So when you use these two ways to get the fibers, in this case the fibers was spoon under the glass slides. So the PLGA is the first picture upside. So the solution now, this red solution is just a rhodamine in water to show the hydrophobicity of the surface. But when you mix the PLGA with polybeta cyclodextrin, the hydrophobicity get a little bit reduced, and the data show us that the surface is more hydrophilic, especially when you use the losartan, a highly hydrophilic drug. The water can interacting a lot with the surface. So PLGA and drug pretty much the same. And when you get these core sheet fibers using PLGA, polybeta cyclodextrin, or the last one, PLGA, polybeta cyclodextrin with the drug in the core, and PLG in the sheet. So you can get now pretty much the same aspect of the pure PLGA fibers, showing us that you can get some core sheet fibers. So thinking on that, we made this kind of proposal using propanolol hydrochloride, using PMAA and polybeta cyclodextrin to get this control release system. And when you see the data, we run some monoaxial and core sheet systems, and the cumulative release from the monoaxial systems, we can see some burst effect in the first hours, releasing about 35% of the drug. But for the core sheet fibers, we can hold most of the propanolol inside of the fibers. So on the right side, we can see the SEM from these core sheet materials, and demonstrating that we can really get these fibers. This work is from Michele, who was a PhD student from Federal University of Minas Gerais. I was a co-advisor in 2015. So once again, after all the time of the drug releasing time, we can get the TEM again from the samples, and the monoaxial system, we can see that everything was dissolved and formed something like a mass of polymers and drug, and that's why the drug was fast released. And now when you compare these with the core sheet fibers hold this structure based on time. So that's what I want to show you. I'd like to thank you, everybody. I will make a special thanks to Professor Frank Alexis. So he came to Brazil a couple of months ago and spent a nice time here. Students learn a lot with him, and we have the opportunity to have some barbecue and eat some picanha. I would like also to thank all the financial support from Brazilian agency and other labs that support the microscopy images and everything. Also, programa de pós-graduação, that is the graduate program you have. And I'd like to tell you guys that now we have a research topic open for submission based on photochromic materials, design and applications. Me, Frankie Alexis, and Professor Sylvia are the editors of this journal, this topic. Okay, thank you.
Thank you so much, Federico. Excellent, amazing work. Federico, this frontier, there will be there are possibilities to waive the fees for some papers or no?
Yeah, you asked me this. Probably yes. We should talk with the Natasha. She invited us for a Google meeting, and I will answer her, and we can ask her for something like that. For sure, we can have a review paper from us, but we should get something like other inviters.
You know, I think 1 or 2 per institution could be really nice.
Yeah, that would be great. We have some really good people working on photochromic materials.
So, look, we're going to open the questions on the chat. Everybody, please, if you have questions for Federico, you can put it on the chat, and then Federico will respond. Thank you.
Yeah, I hope I was not too fast and my connection was okay. And nice lecture, thank you. Are some of your drug delivery system near to the clinic phase? Yes, that's a good question. Sorry about I don't know your name, but okay, thank you for the question. Yes, during my postdoc, I removed some slides. It was too big my presentation, as you told. I have worked with some angiotensin supramolecular system, and these angiotensin 127 and all these peptides are in phase 1 and some phase 2 in clinical trials. So now we have submitted a proposal to we have some proposal because they have some evidence that ACE ECA2 system can be related with coronavirus. So this supramolecular system has been used for peptides. The pharmaceutical company that hired me in 2003 to 2006 pay me to develop something like hi Paul Juan, and pay me for 3 years to develop some antihypertensive drugs based on snake venom peptides with the drug. So this was not running. They stopped this trial. It's getting too expensive to get these peptides. but angiotensin it's phase 1 and phase 2, depending on the angiotensin 1 to 7, angiotensin 2, or the modified ones. So my experience with frontiers is they proposed me to lead ASP, however, I was the fees would not be. Oh my God! I hope they can change their mind and they can waive some papers. But let's see. Let's see.
Any other questions? Federico, you see these supramolecular systems going more for the biosensor application or the drug delivery applications?
For biosensoring, it's not. It has been applicable a lot, but drug delivery system. There's a professor from now. He's in Cornell University. He's using for something like this, but more based on poly beta cyclodextrin system. So it's a polymer based on cyclodextrin units. So not just the monomer as I have shown.
You have a question from one of our students as well.
Yeah, thank you for the excellent presentation. What are the current challenges in use from molecular systems? So, Lisbeth, the big point is to figure out how to understand your system. You can go online, read a lot about other systems, get informed, but when you change the molecule, you have to do, or you should at least run all the characterization prior to go to in vivo or in vitro experiments. I guess the biggest challenge is you must be familiar with thermodynamics, structural characterization based on chemists, and that's the biggest challenge, I guess. But it's beautiful because you have so many informations from usually water solutions. So there is no color changing like I showed that photochromic devices. There is nothing like this, but you have some physical and supramolecular informations really nice based on intermolecular interactions. So the biggest challenge is go deeper in your system, but it's nice to go for it.
So it really seems, Federico, that for this kind of systems, you really need to have this computational chemistry data to
For
understand.
sure, for sure, it helps a lot. This collaboration with theoretical calculation, it's crucial to get the information because you actually can see and prove the interactions, why they are interacting more than the other systems. So but it's the biggest challenge when you have this kind of collaboration. I can talk by Juliana now because I'm as a experimentalist researcher, I run all the experiments and get a doubt in the end. So I went to these theoretical calculations researchers and say, I have these questions. So it's take too long to get the answer. It's nice when you have the question and you can run all the data at the same time, so you can learn much more uh, based on this collaboration than just ask a question at the end of the day for your colleague and your collaborator. So, but it's crucial to get this kind of information. Usually in the journals, they asked us to do you have theoretical calculations based on DFT or molecular dynamic simulations, or whatever.
Excellent. Any other questions from the professors or the students? So what is your next big project, Federico?
Finish my house. No, I'm kidding. My biggest project now, it's been related to the photochromic devices. So I'm still looking for your samples, your cellulose material. But no, I'm kidding. Yeah, no, I'm really waiting, but I'm kidding. I'm not asking you now about this. But yeah, I guess the biggest challenge now is working more with these photochromic devices and put in more applicable to sensoring, or I don't know. I guess is this.
Yeah, I hope we can send you the sample soon, Federico.
Yeah, and I hope I can go to Yachai.
Yeah, we are
It
waiting
seems
for you.
okay.
It seems that there is no additional questions. Thank you so much again, Federico, to take this time at night.
Okay, don't worry.
Please say hello to your family. Thank you to
Okay.
you who were able to join this webinar. And we stay in touch, Federico, and
Okay.
you have a good
Thank you for
weekend.
the opportunity. Thank you really for the opportunity.
Take care. Bye-bye.
Okay, bye bye.